Bien, bueno, es un placer retomar los seminarios que hemos tenido un seminario poco tiempo por distintos motivos, pero retomar el seminario esta semana del IMC con nuestro invitado internacional, Carlos Pajas, que va a estar acá en la Católica por un tiempo. Entonces, si quieren acercar a él después, también lo pueden conocer por cosas. Claro. Bueno, Carlos hizo sus estudios de pregrado y doctorales en España. Sí. En el 2009 tuvo un doctorado en Barcelona, siempre en Barcelona. ¿Sí? Barcelona, sí. Y luego se vino para acá, para Chile, dio el salto del Atlántico. Ha estado en la Universidad Técnica Santa María, aquí al lado. Pero acá siempre. Acá en San Joaquín, sí, camino agrícola. Aquí al lado, hasta el 2021. Ahora sí, 2022. Y ahorita acaba de ser contratado en el Barcelona Supercomputing Center. Entonces, pero está ahorita. Está en Chile, está aquí en la Católica. Bueno, su especialidad es en métodos numéricos, solución de ecuaciones diferenciales con métodos numéricos y en ciencias en general. Y es uno de los temas que nos va a hablar hoy, del método pseudo-spectral para simulaciones en acústica de cuantos. ¿La hago en castellano o en inglés? Yo creo que en inglés, por si acaso. Okay. So, thank you very much. Y un aplauso. Okay. Yeah. Thank you. Today, thank you very much for inviting me, and I'm very happy to be here and to present some things that I have developed in my PhD and during my research life. And today I pretend to do a very pedagogical talk. I would try to explain the pseudo-spectral methods, the subtleties of the methods, which problem we can find whenever you want to implement something in pseudo-spectral method. And the context would be room acoustic simulations. And room acoustic simulations, I choose this because it was what I did in my PhD, but also it is because it is a very mathematical, in the mathematical point of view, it is a very interesting problem because we have complex boundary conditions, we have an hyperbolic equation with propagation, and we have to implement some kind of punctual sources. So we have to deal with all the problems that someone can find whenever you are implementing something in numerical. Okay, so the context is very interesting in the mathematical point of view. So I divide this talk in 3 parts. Okay, the first part is just an introduction and some concepts to understand what we are going to do. Then we are going to see the main topics that we find, that we face when we try to implement some method, independently of this pseudo-spectral or finite element or finite difference. We always have to deal with these 3 problems, which are wave propagation, source generations, and implementation of boundary conditions. And we will see the subtleties that we find in pseudo-spectral, always compared to finite difference, which is the standard, and I think that most of you know well. Finally, we have the last part where I have to explain some constraints that we find in pseudo-spectral methods that we have to take into account, and finally some outlooks and things, conclusions derived from this talk. Okay, so let's start by the introduction. Okay, let's see first which is the objective of room acoustics. Room acoustics, what the main goal of room acoustics is, they want to compute the input response of any closed environment. Imagine we have this kind of room, okay, where we have a source and a listener, okay, and what we want to get is the input response, the information of the room, which is obtained due to the input response. Observe that the input response typically in room acoustics have 3 parts, okay. We have first the direct sound, which is the sound that goes from the listener to the receiver, right? From the source to the listener, sorry. Then we have the first reflections, which is the sound that has only reflected once at the walls and ceilings of the enclosure. And at the end, we have the later reflections, which are reflections that has been more than once in a wall. And with these 3 parts, we are able to characterize the main features of an enclosure. Okay. Typically, the reflections will give information of the geometry of the enclosure, whereas the late reverberations will give information of the impedance properties of the walls. Okay, with these two information, we are able to know how the enclosure will be and how the sound will be affected by this enclosure. Okay, so if we are able to take this information, we are able to know how the enclosure propagates the sound. And this is very interesting for auditorium or for buildings that are not already constructed, and you want to know how it sounds before it is constructed. And it is very important to make simulations of that and to have an idea if it is good or bad, the proposal of the room that is going to be built. Okay, so it is important to have an expertise and to know how to implement these kind of simulations. These simulations also are very difficult because we have to implement these sources that are punctual. We have to propagate this source like with an hyperbolic equation, like the wave equation, and at the end we have to characterize these boundary conditions that we will have. We will do it through an impedance boundary model, and also we should consider the normal vectors of these surfaces. Okay, and with this we will be able to characterize the full problem. Okay, another important thing, we have two different approaches in the computational methods in room acoustics. There are the geometrical methods and there are the numerical methods. Geometrical methods, the typical are the ray tracing methods, image source method, beam tracing, whereas in numerical methods we find finite difference time domain, digital waveguide mesh, pseudo-spectral, finite elements, you know, the typical methods. Okay. In this talk, we are going to focus only on the numerical methods and only pseudo-spectral and finite difference. Okay. As I said, geometrical methods are very simplified methods. They assume that the sound propagates as a ray that rebounds all over the room, and phenomena like diffraction or interference is not characterized, at least directly. They can incorporate these phenomena, but not in a direct way. Whereas the numerical methods, we don't approximate the wave propagation. We solve the wave propagation as it is, with the wave equation in this case. And at the beginning, at the end, it would be more accurate algorithms, but you will spend more time of computation because they are more expensive than the geometrical approximation. As I mentioned, we focus here in numerical methods in the time. Okay.
So what do you mean exactly by geometrical methods? Like what?
Ray tracing, for example, what you do is to treat sound like if it was light. Okay, and you just through rays of sound that they rebound into the walls with the specular laws, doesn't matter what, but you consider as if it was ray of lights.
Like particle calculation.
So, which are the things that we need to do if we want to solve the problem? We need to state the partial differential equation that we are going to solve. We need to define which tools, which numerical tools we are going to use in order to approximate these partial differential equations. And it is very important also to have or to design good experiments, numerical experiments, in order to compare the different numerical techniques that you are going to use. In this case, we're going to compare finite difference with pseudo-spectral methods. We need to define proper experiments that give this information that we demand. Okay, let's continue with the physical background. Okay, let's see which physical background is needed to state the mathematical and physical problem of the sound propagation in a room, an enclosure. Imagine we have this square represents a room, okay? We have a listener and a source, okay? And we have the domain and the boundaries, okay? So what we define, formally, what we define is the pressure and the acoustic velocity is defined in the whole domain, okay? And what we are going to assume is that the source would be a punctual source, like a Dirac delta function, okay? But we need to approximate it in a numerical point of view. But what we want to do is to propagate a Dirac delta function into this domain And what we are going to get is the Green's function of the system. That is very useful because with the Green's function, you can do whatever you want. Okay? You can introduce the source that you want, just convolving this Green function with the source that you want, and you will have the sound, but with the echo of the room. So it is very interesting, this Green's function. Okay, so let's first, which assumptions we are going to take in order to get the partial differential equation, in order to get the wave propagation equation. What we are going to assume is that in a room, the temperature and the density is constant in all the room. Okay. We also assume that the air is a stagnant fluid and it is not perturbed before the source emission. So we have a perfect fluid in the room that has no wind, no nothing. Okay. So with this, we can assume the linear wave equation as a equation for propagation. Okay. Another thing that we are going to assume is that the walls will be characterized by a locally reacting impedance boundary model. We will see later on how it is stated, but at the end is the most simple way to characterize a wall. That is assuming just the specular and the specular laws that we will see later, but it is the simplest model that we can assume in a wall. We are going to assume. Okay. For the wave equation, okay, what we have, well, this is not maybe written, but I'm going to, this is the gradient in the normal direction, the divergence in the normal direction, or the vector nabla in the normal direction. We will see that I didn't write really accurately from the mathematical point of view, but let's see. What we're going to define, define according to the assumptions that I tell you before, is that for the propagation in the air, we're going to assume the wave equation. For the source generation, we are going to assume a unit input signal, a direct delta function. And for the boundary conditions, we're going to have this impedance model where this Z is the acoustic impedance and is the characteristic of the material, the acoustic characteristic of the material, okay? This N is the normal direction of the wall, okay? And in this case, we only have the acoustic pressure because we are using the wave equation representation, okay? However, we can use the Eulerian representation, which is exactly the same, it's analogous. In this case, we have two equations of first order to characterize the wave propagation, which is the linear Euler equations. We have the velocity in the pressure, acoustic pressure, and again, we have a unit input signal that we want to simulate, okay? And here we write the boundary conditions that, again, this normal vector should be here. It was written that. What I want to say is this is fulfilled only in the normal direction of the wall. Okay, this is the meaning of this equation.
This is a mixed form of the previous.
But
it's the mixed form of.
It's the same. It's the same form than the previous one. Okay, but in this case we have pressure and velocity. In the other case, if you substitute this and you put here, you obtain the equation exactly. Both representations are completely analogous. Okay, and we can use the wave equation or the Eulerian representation is exactly the same. And we will see in pseudo-spectral methods and infinite different representations using both. Okay. Okay, so finally, to end this first part, okay, we have a goal, which is the goal is to transform these partial differential equations into an algebraic system of equations, to solve it in an algorithm, in a computer. And what it is very important, and I think that it is very important in any numerical method that you face, independently of the method that you do, is to separate your numerical problem in small numerical problems and treat it separately. Because if you treat these things together, you probably fail or you will not see what you want, okay? So it is very important to treat the wave propagation as one problem, then the source generation is another problem, and then the boundary conditions. But always the experiments that you want to do, if you want to observe some properties or some feature, try to separate these problems and to design experiments that only shows the propagation, the boundary conditions for the source generation. It is very important, this, and I want to emphasize this, because is the key of the success, is to split the big problems into small problems, okay? And
can you go back 1 second? We are assuming these constants are homogeneous everywhere, right?
in this case, yes, because in a room, we assume that the density, the velocity, the temperature is quite constant, and there are no wind, and the fluid is stagnant. Yes, we can assume it, okay, but only in closed environments, and I don't know if it is really true.
Yes.
Okay, so let's go to the talk. Okay, so now with this background, we are ready to talk about the wave propagation. We're going to see the algorithms, the finite difference algorithm, the pseudo-spectral algorithm, for the Euler, for the wave equation. And we're going to study the dispersion error, which is the thing that it is very important in room acoustic also, because at the end we want to see how it sounds, how the sound propagates in a room. And it is very important, the dispersion, because dispersion error would change the frequency of the sounds and maybe would give us bad information. So we need to control very good the wave propagation and the dispersion error reduced due to the numerical approximation. So I'm talking very pedagogical things and things that I'm sure that you know, but it is important to learn. Once you want to transform these partial differential equations into algebraic equations, the first thing we need to do is to discretize our domain, okay? No matter which. In this case, it's a centered mesh. We can do a staggered mesh. There are a lot of meshes to do. But in pseudo-spectral and finite difference, there are regular meshes, okay? We have only one spatial sampling and spatial sampling. And it simplifies a lot the domain, maybe. If the geometry is complex, we will have some problems. But it simplifies a lot the algorithm. And if you want fast algorithms or something like this, typically regular meshes would provide you algorithms that would be very fast and easy to implement. In this case, since we are talking finite difference and pseudo-spectral, we use Cartesian meshes. Could be staggered or not, no matter. And what we do is to discretize the variables, the pressure or the velocity. We discretize the space and time. Okay, the position of the mesh we only measure at some specific positions and at some specific times. Okay. So once we discretize the domain and we discretize the space and time, we are able to approximate the partial differential equations into simple algebraic operations like subtraction, divisions, multiplications, these kind of things, products. So this is the real problem, and what we get at the end is an approximation with a discretized mesh, discretized variables, and approximated finite difference or pseudo-spectral operators. Okay. So in finite difference, the thing is that we do in general is to approximate these partial differential operators into simple algebraic operators where we have a subtraction and a division and something like these things that we can program. Okay, this I don't know how to program it. This, yes, I know how to program. However, every time that we are approximating these partial differential operators, what we get is something that is approximated. It is not the absolute truth, and sometimes we know how it is approximated, this value, okay, and how the error goes. It's very important to have control of this because at the end, when we are approximating and we don't know how to compute this exactly, we always have some kind of error. So it is important to know the errors. Here there are some examples of finite difference operators. And in this case, for example, for the wave equation, the classic algorithm, no? We have a second order temporal derivative, second order spatial derivative. What we do is to apply just second order finite difference operators, and we just put on the equation, and what we obtain instead of a partial differential equation, what we obtain is an update equation that we can compute the values of n+1, the instant n+1, as a function of values of that depend on n and n-1. Okay, this combination of values provides us an update equation that we can compute the values of the pressure in all the domain, not all the domain, because the boundaries here are not taken into account. The domain only that considers the air or the wave propagation. Okay, this is very classical, I think that you know. And here, for example, we have this is the classical stability Courant number. Okay, and I think It's very easy for you, this is just an overview. For the Euler equations, we can define this, okay? It can be defined like this or in a staggered mesh is analogous because here when you are implementing is exactly the same. However, you need to shift the spectral derivative. You need to shift by a factor, by a phase, the spectral derivative that you compute here or here. But now we are talking about finite difference. We will see later into the spectral.
I mean, in the case of a staggered mesh, you have to put the...
In the staggered mesh, because here I write like if I were programming this,
right?
Okay, so there is no 1.5 and something like this, but this n+1 should be n+1/2, and these positions with v sub x is e plus 1/2, yeah. J plus 1/2, and k plus 1/2. But the algorithm is exactly the same. If you want to take the dispersion error with this, you take exactly the same dispersion. And when you program, you don't have 1/2. You work with 2 vectors, with 3 vectors. So yes, but maybe it's good to mention that it is stated in the staggered mesh. Here again, we have the stability current number here. Okay? And well, this is the classical finite difference algorithm. So, what we do for the wave equation, we use a second order central finite difference operator in time and in space, whereas for the Eulerian representation, we make a combination of a backward-forward finite difference operator that at the end, what we obtain is an algorithm that is exactly the same in terms of dispersion, accuracy, and error. Okay, for the representations are completely analogous. Now let's going to see the same that we see for finite difference, but using pseudo-spectral methods. Okay, now we are going to increase a little bit the. So in this case, for the time derivative, we are going to use exactly the same approximation that we use in finite difference. We're going to use finite difference operators, but the difference is in the space. The space, we're going to use Fourier techniques. We are going to derivate the function using Fourier transforms. We're going to use the properties of the Fourier transform. We know that if we have a spatial distribution of nodes, okay, if we make the Fourier transform of this spatial distribution, we are in the Fourier space, in the wave number space. If we multiply each wave number node by each wave number associated, and we come back and making the fast Fourier transform, the inverse fast Fourier transform, what we obtain is exactly the operator. Not exactly, but an expected accuracy. We get the best accuracy that we can get, and we can get the spatial derivative of the variable t. Okay, there are some assumptions that we need to know, but the essence is this: that if we have a spatial distribution, we can just make a Fourier transform, multiply by this number, and come back, and what we get is the Fourier transform. Okay, the Fourier transform, the spatial derivative. So, similar as for the finite difference, for the temporal derivative, we use a second order, in this case, finite difference operator, whereas for the spatial derivative Laplacian, what we do is to apply these techniques of the Fourier transform. Instead of using finite difference operators, in this case, what we do is the fast Fourier transform in the x direction, we multiply by the wave number associated, and at the end, we make the inverse fast Fourier transform in the x direction. We do the same for the y direction and for the z direction. You are able to compute these quantities, you get the spatial Laplacian of these quantities, and with an accuracy that would be the best accuracy that you can get with a finite difference operator. So this is the optimal way of computing spatial derivatives. Again, for the Euler equation, we have the same things. Okay. Observe that in this part is exactly the same as the algorithm that I presented before for finite difference, and here we have how to compute this spectral derivative using Fourier techniques. Okay. So, what is important? The stability. No? When you are working with this kind of algorithm, you want to see if it is unconditional stable or not, or just. In this case, these algorithms that I present you are explicit algorithms, and they have stability. They have stability limits, and you cannot use temporal and spatial discretization that you want. You need to fulfill at least these relations of here if you want to succeed in your simulation. Okay? In this case, what we see is that finite difference get this stability, which is the dimension of the spatial dimension of the problem. Okay, and for this, and so the spectral we get this relation of here that at the end we have a factor of 2 over p of difference. Okay, and what we see is that, for example, for the spectral time domain methods, we can get stable simulations using larger spatial samplings, which is the first thing that is better than finite difference. Okay, for example, in finite difference, if you have I don't know a plane wave with a certain wave number, you need at least 7-8 points per wavelength in order to characterize this wave. Whereas in pseudo-spectral methods, we need only 2 points per wavelength to characterize the wavelength, because it is the Nyquist theorem at the end. The Nyquist theorem is just a man, 2 nodes or more to characterize any wavelength that you design. So if you are using pseudo-spectral techniques to compute spatial derivative, you have less restrictions than in finite difference, because this Nyquist theorem, and you can use larger spatial samplings. Let me see. Another thing that I want to say that is not here is, okay, we can use larger spatial samplings, but there is a trick that is not said here, is that, okay, if you have a simulation in finite difference and in pseudo-spectral, surely simulating the same plane wave, simulating the same problem, we will use 4 or 5 times a bigger mesh in finite difference than in pseudo-spectral. But on the other side, finite difference always work at the limit of this stability current number. So given spatial sampling and the limit of stability current number, what you get is a temporal discretization, some temporal discretization. And for pseudo-spectral time domain, we typically don't work into the limit of the stability current number. We work in a very low number compared to the limit. Okay, because if you work with the limit, what you get is simulations that gets a lot of error in the temporal part. Okay, so at the end, yes, we can increase the spatial sampling in pseudo-spectral, but we need to reduce a lot the temporal sampling. So yes, we have meshes that are smaller in terms of nodes in pseudo-spectral methods, but we have to do more computations of the results in pseudo-spectral than in finite difference. Finite difference, since they work in the limit of the current stability number, they provide temporal discretizations that are higher than the pseudo-spectral. Okay, we will see now when we are going to analyze the dispersion. But
the cost in general is higher for the spatial solves.
I think it's better to have smaller meshes and to do it a lot of
smaller time sampling,
yes, than to have a very big mesh, but you have a bigger temporal sampling. Yes, because at each time you will demand more nodes. I think it's better to have less nodes and do it a lot of time if you parallelize or something like this. Okay. So what is dispersion error? I know that, I'm sure that you know it, only to have this pedagogical talk. Okay, dispersion error, at the end, if we're doing in the analytical case, we have the wave equation. This is the wave equation without no finite difference operator, without nothing. This is the wave equation only. And what we do is to introduce a plane wave, okay, a plane wave into the system. If we manipulate this and we calculate this, what we obtain is that the velocity or the wavelength has a linear relation with the frequency, and this linear relation is constant and provides you the velocity of propagation. Okay, it happens analytically, and what it says is the sound propagates isotropically and independently of the frequency. We always get the same velocity of propagation. Okay, this is what we obtain in the analytical world, and in the real world, if it is homogeneous and everything is perfect. Okay. But what happened in the numerical case when we do a finite difference algorithm, finite element algorithm, pseudo-spectral algorithm. What it happens? We don't have the wave equation. What we have is an update equation, which is different. And if we introduce a plane wave, it is not exactly a plane wave, it's a numerical plane wave, which is discrete. You do this, that is very similar from the previous case. You obtain something that is not the same. In this case, you don't have a linear relation between the wavelength and the frequency that multiply it, provides you the numerical, the velocity of propagation. In this case, you get such a complex function that depends on the wave number, the frequency, the angle, the solid angle, the Courant stability number, and it provides you a numerical velocity of propagation. In this case, what we obtain is something that is not isotropic, and it strongly depends on the frequency. Okay, so just simply to if you take the wave equation and you discretize it and you do some numerical approximation, you have this. Independently of the method you are using, it could be the best method that you can imagine. You will get this, okay? Not the previous thing that I showed you that was this. And what we want is this, okay? But we get this, okay? Another thing, important thing is, depending on the numerical method and the approximation that you use, sometimes you cannot get in an easy way this expression that you want, okay? It's not the case on finite difference. In pseudo-spectral, we can get very easy expressions, and we will see, okay? So, another thing that I told you before, that whenever you are dealing with numerical methods, it is very important that you can design a numerical experiment that can measure these things. In this case, we are trying to measure the numerical dispersion error, okay? Well, it is very interesting if you can design an experiment that you can run a simulation and you can obtain values that confirms this, in this case and in the boundary conditions and everything. So here, what we design is an experiment with the idea to fit this dispersion error whenever you are using a numerical scheme. Imagine you have this mesh, a very big mesh, and this line up here are nodes that are stimulated with a plane wave, a sinusoidal, with a certain omega, with a certain frequency, okay? What we expect is plane wave propagating with this direction, and the wave number of this plane wave would be different than this relation. We won't get this. We will get something more similar to here. So what we want to do is an experiment, okay? We check at the normal direction of this plane wave, and what we get is something like this, but observe that we have very few dots. If we try to make an interpolation of these dots, we obtain something that is not good, and the values of this numerical wave number are not really accurate. So we need to increase somehow to get more samples of this wave. And what we do is just to take the idea that the plane wave has symmetry in this direction. And what we do is just project the information of this field and these nodes into this line. And what we get is something like this, okay? And we can measure in a very precise way the dispersion error of any algorithm that you want, and with any orientation that you want. And you can change this orientation, and you can do this same procedure. And at the end, what you get is a sinusoidal with a lot of samples, and the measure will be very accurate. Okay.
This is in relation to what? Like, what you measure the frequency here?
No, I emit a plane wave with certain frequency, and what I measure is which wave number I get in the space.
Okay, and you compare that to which wave number?
No, because I know that theoretically,
okay,
the relation is like this.
You put a source where you know what the wave number is, and then you.
I put the source with the frequency in time, but this propagates through the space.
Yeah.
In a space where I get is wave numbers, not frequencies.
Yeah.
And I know there is no linear relation between frequency and wave number, because we have discretized the domain and these are an algorithm. So I get for a given omega and a given angle, which is the wave number that I expect. It's some kind, I measure the dispersion error without knowing which is the explicit dispersion error. Do you understand? sometimes infinite elements or another method that you cannot compute this dispersion error is very useful, this experiment, because you take the number of which is the dispersion. So in finite difference, there is no problem. We can compute this dispersion error. This is the standard finite difference dispersion error. Observe that we don't have a linear relation between the wave number and the frequency. There is no linear relation. In this case, we have a strong dependency in the angle, in the sinus is up to 2, and the angle. It is not a linear relation. Here we have the stability current number, and this that can be expressed as omega also. But here I put all in terms of this and lambda, which is this number here. So at the end, we have a more complex relation that we expected, and we see that it depends on the frequency and in the angle. So the velocity of propagation depends on these two parameters, okay? Here this is the experiment that I told you before. I take different angles, okay? And this is the analytical curve of the dispersion error, the dispersion error computed analytically. And you observe that the experiment is very good and works very fine, okay? We see that now the velocity of propagation is not isotropic at all, okay? We see that it depends on the angle, and also here, this plot is with one frequency, and this is with another frequency. You observe that the values change of the numerical dispersion error also. So
that C, where did you get it from? The C, not the C, no, but the C. The C?
C is the expected, the theoretical.
Okay. So that the
isotropical one, yeah, what you expect. Okay. Yes, because we know that we put it. It's 340 or whatever this is. Okay. Very important. In finite difference, what we get are subsonic algorithms. We can get at least the velocity of propagation C or less, not more. Okay. So the spectrum will see that is different. They are supersonic algorithms. Okay. Okay, it's on the spectral time domain. The first thing that is very interesting here is that we have a dispersion error that does not depend on the angle, only depends on the frequency and the wave number. It is more simple. In this case, we get always isotropic dispersions, but we have dispersion that depends on the frequency. Okay? This is not possible to eliminate, but we eliminate the angular dispersion that was a problem in finite difference. This is the one thing that Pseudo-spectral is very good. Here we observe this is the angle, and this is isotropic. It does not depend on the angle.
What boundary conditions are you using?
No boundary conditions. We are only taking into account the wave propagation problem. I make a huge domain. You can put zeros if you want at the end of the domain, and I make a simulation and I measure in a region that I'm sure that the sound will not rebound onto the boundaries. So they are expensive simulations in terms of that you need a huge domain, but are very simple. But what we do is just stimulate a line of nodes with a sinusoid. And at the end, we measure in the middle in a specific region that I'm really sure that no sound comes from anywhere. And if you do like this, you can obtain these measures. Okay? So here we are not dealing with boundary conditions. And what we need, if you want to measure the numerical dispersion error, you need to work in the wave plane regime. So to build this in a simulation is not trivial. You need to make very huge simulations, measure in a small region in a short time, and at the end you obtain these measures, but they are not trivial. In this case, so we get a numerical velocity that this is isotropic, and always the numerical velocity is greater than the expected velocity. In pseudo-spectral, we get supersonic algorithm. Okay. Observe that depends on the frequency. If we change the frequency, we get different values of the numerical dispersion. It is not angle anymore. This is the NT, which is the period divided by delta t. Okay, another way of doing things. But we have isotropy, but we have a strong dependence on the frequency as we so. This is a summary. Just on the wave propagation, we get two algorithms, a finite difference, so the spectral algorithm. And what we see is that, okay, we have finite difference sorry, pseudo-spectral methods allows larger spatial samplings. However, the temporal sampling would be smaller in pseudo-spectral than in finite difference. The dispersion error, we have analyzed it, we have studied it via analytically and via numerical experiments. And what we see is that pseudo-spectral methods has isotropic dispersion error instead of finite difference that is not isotropic, and it strongly depends on the angle. And both methods had a frequency dependence dispersion error, okay? From here, we have something, but we have just talked about wave propagation, not sources, not boundary conditions. Okay, now we're going to talk about the source generation. Okay? Our goal in this problem, what we want to do is to compute input response, Green's function of environments. So Green functions are defined due to Dirac delta function. We need to define a Dirac delta function. The problem is that when you try to do it numerically, it's too singular, this function, and you need to approximate somehow this function, because if you put it as, like this, you will find bad results, okay? In our approximation and our study, we decided to work with two different candidates of Dirac delta function for low frequency range. The first one is the Gaussian pulse, which is typical. Well, in this case, and the sinc function, okay, we will see. Here you see you have a Dirac delta function. If you do the Fourier transform of the Dirac delta function, what you obtain is a constant. Right? What is telling to you is that this function here emits exactly the same energy per frequency. Each frequency is emitted exactly the same energy per frequency, and it is transformed in this function that is very singular. Okay. Okay. What we want to do is some approximation for the low frequency range, not for the magic from here to here. In this range, we want to get something that is similar to this transformation. Okay. We will get some Dirac delta function for low frequency ranges. Okay. The Gaussian pulse, for example, if you do the Gaussian pulse, depending on the bandwidth of this, we get a transformation with bigger or smaller transformation, but in this range of here, we can assume that is similar to the Dirac delta function. The transformation is very flat here. You can say, okay, in this range, these sources are very similar. And on the other side, we have the sinc function, which is this function. And we can control with the frequency. If we put the value f, in this case is 2,500, more or less. If you put the frequency, you will get that it's flat from 0 to the frequency that you put here. Okay. And then we have this because we have filtered the sinc function. So that sinc function goes to infinity, and we have window it somehow, and you observe it here. Okay. But in a low frequency range, we obtain somehow a Dirac delta function. This is a Dirac delta function in this range. So it's useful if we make a simulation with this function or the Gaussian pulse. What we obtain would be the Green function only for this range of frequency, okay? Which is the range of frequency that we are interested in. At the end, we prefer the sinc function because it has a flatter spectrum in the frequency domain, and also the frequency that appears in the sinc function is exactly the frequency that you put in your bandwidth. Okay. Yes. See, the Gaussian pulse emit more indecided energy because you cannot control exactly the frequency. There is a parameter that is related with the frequency, and it's not the same as the sinc function. The frequency is the frequency, and it goes from 0 to the frequency that you put. Okay, one important thing, in general, not in pseudo-spectral, in general, we find these two ways of introducing sources in a numerical scheme, okay? You can introduce hard sources or soft sources, okay? Let's see which difference they have, okay? The hard source is just to introduce, you have a function that you want to introduce in the numerical scheme, and you forget about the update equation and just pressure is equal to this function. You put this, like this, hard function. A hard source, and these hard sources, basically, they are not based in any physics, they are not based in any mathematics, they just introduce it like this, and they just diffract the sound that interacts with them. If you have a hard source and it emits, and then the reflections that come here, it diffracts the sound field instead of the soft sources that they don't diffract the source field. Okay? And another thing important is that soft sources are based on the physics. Okay, you can mathematically derive where they come from and what it is. And they just, you have the pressure equal to the update equation plus the function that you want to do. So the main difference between currents of sources is the way that you introduce it in the numerical scheme and the things that they happen in the simulation. It happens different things, okay? So you need to consider this. Another important thing, in finite difference time domain, we can implement punctual sources. Also in finite elements, we can do punctual sources. So the spectral methods, if you introduce a punctual source like this, you get a thing that is an error that is like a Gibbs phenomenon that appears. Let's see why. If you make this punctual source, you get, and in all the nodes of this axis and this axis, you will get this error of here that appears. Okay? Why? Why it appears? Because now we are making a spatial derivative. Okay? Spatial derivative. We take this line. If we want to compute the y derivative of this dot, we need to compute this, all these nodes. And for the x component of the derivative, we need all these nodes. In this case, you are introducing one punctual source. And what happens to Fourier space? In Fourier space, we need at least 2 points to have to characterize the minimum wavelength that we have. In this case, if you only have 1 point to characterize the sources, you are failing the Nyquist theorem, because you would need at least 2 points to say, this is a source. The minimal source that I can put you is this, 2 nodes of source, no one. One violates the Nyquist theorem. And what happens is this error is aliasing frequencies that are transformed to other frequencies that are not true. And they appear because you are only putting one node, not frequencies, wave numbers, sorry, because we are in the space, okay? But you are putting wave numbers that doesn't exist and it transforms into another that they exist and it changes. The solution, you need to put a volumetric source with at least 2 points per wavelength at each direction. If you do this, you avoid this error, okay? And it's very important. So the spectral is mandatory to get these volumetrical sources at least with 2 points per wavelength at each direction, okay? If you don't do it, you will have problems. More or less what I tell you, so fast. And a summary of this, we see that maybe the same function is the best candidate to obtain impulse response because we want to obtain green function, so it seems reasonable. Finite difference, it is important to observe that allows punctual source generation, whereas pseudo-spectral need volumetric sources to implement. Okay, this is the main result. Finally, let's see the boundary conditions. Okay, remember that we are computing input responses in rooms, so we need to characterize the walls of the enclosure. Okay, basic assumptions. How we are going to design this impedance boundary model? We are going to assume that particles in the wall do not interact with them, are separate. Okay, and the acoustic pressure and the particle velocity are related with a linear constant, which is called impedance, okay? There is, and also the normal direction of the wall, it is very important because is where these properties are fulfilled, okay? At the normal direction only. So, this is the model that I showed you before. Here we have a wall with a normal vector at the x direction. We have an incident wave that is impacting into this wall, and what we expect, this incident wave impact to this wall with an angle theta, and what we expect is a reflected wave with certain amplitude and with the same angle theta. This is the simple model that we can imagine for a wall, okay? Okay, and this impedance boundary model, if it is well stated and well, what we get for a plane wave is that giving an impedance characteristic of the material, acoustic characteristic of the material, and giving an incident angle, what we get is the reflection coefficient that we get, the amplitude of this reflected pressure, okay? So we can control, given acoustic properties of the material of the wall and the angle of incidence of the plane wave, what we get is the reflection coefficient that we are getting for this for impacting a plane wave into a wall. Okay. This is the Eulerian representation, and we will see the Eulerian and the wave equation representation. Okay. For the wave equation, what we have is this is the equation that we have at the boundary, that is fulfilled at the boundary. And what we do in the model that we presented is to derivate in time this equation, because it was for stability reasons, we need to do this. And with this equation, we can compute a boundary condition equation. But in this case, we need to combine, we can only build this using finite difference operator. Okay? So at the end, in pseudo-spectral, we will have an hybrid method. For the wave propagation, we have pseudo-spectral, and at the boundary, we will use finite difference approximation. But we will see now. For the wave equation, we use first and second order set and finite difference operator. As I tell you before, for this equation, we don't use pseudo-spectral method, we use only finite difference approximation. We use, to characterize the normal vector, we use a forward-backward finite difference operator, depending on the direction of this normal vector. We need to combine these forward-backward operators. And, well, let's see more. In this case, this is the update equation for the boundary in an X wall, okay? Let's see by parts. Here we have the acoustic impedance, okay? Let's see, this is the pressure at time n minus 1. And here, wow, a pressure at time n plus 1, okay? This is one of the, no, it's not the problem. Look that these pressure values are always in the wave propagation mesh. This node is not the boundary nodes, you know, wave propagation node. So what we do in these kind of problems, we will first compute the values of the pressure in the wave propagation nodes, and then, as a second step, we compute the values at the boundaries, because this value has been already computed with wave, okay? So as you see, it changed a little bit the things. You cannot do what you want here. You have an order. If you want to compute this value, first you need to compute this value. You cannot do it in another way. Have restrictions. Also observe that this it used finite difference operators. So we don't see here any Fourier transform. And it provides some errors that we will see later. On the other side, what we develop, it is important to notice that the previous scheme for the wave equation of the integration for the boundary conditions and these didn't exist before my contribution to the wall, and this was something that it was not developed, and actually I think it still be an open problem to define proper impedance boundary condition for pseudo-spectral methods, because it's really difficult. So this is somehow the research that I've done in the PhD. And in this case, for example, what we try to do is to implement a boundary conditions instead of the wave equation. We wanted to design a boundary conditions that works and were stated in pseudo-spectral methods. So it was the motivation for this. In this case, these are the boundary conditions. I'm going to explain. These are called semi-empirical boundary conditions because there are no mathematical foundation. There were some kind of embedded, constructed manually. What it considered is a parameter that it can go from 0 to 1 or from 1 to infinity. It changes the equations. This parameter will take into account the amplitude of the reflected wave, and we also take into account the normal direction of the wall, just computing the Laplacian at the normal direction. Here there is no Fy, Fz. We only compute the spectral derivatives in the x direction. If we take into account the normal direction in this pressure update equation, and we take this parameter, we can reproduce somehow this impedance boundary model. Okay, and when this value is greater than 1, instead of multiplying here, what we do is to divide in the velocity component that the wall is. Yeah, 3 minutes. Okay, ¿cuánto? Entonces vamos por feina. Vale. Okay, this is the scheme that I find in Fourier transform, and this is the infinite difference. We can use it in finite difference and in Fourier transform instead of the wave equation that cannot be used in pseudo-spectral, or can be used, but rewriting the formulation.
In finite difference, can you have a oblique wall?
No. Here is only for rectangular walls. No. At least for this formulation. Well, finally, there is a relation with the impedance of this parameter. Okay, and I'm going very fast. Okay, and the experiment that I wanted to explain. What I do is a simulation, a huge simulation again, and I put a wall, and I put a source very close to the wall, and I measure just in alignment here, and I take into consideration that no reflections are there, and you can measure this reflection coefficient by each receiver would be the angle. And if you emit a sinc function, for example, you will have for each frequency that you want. Okay, and here are the results. And in pseudo-spectral, we've said that in a there is a very big range that the results are not better than finite difference, because here in the wave equation we have an hybrid formulation. So I'm very fast. Wait a minute. And for the Eulerian formulation, we get better results for pseudo-spectral, but here we have these artifacts, but it was because I did this experiment with a punctual source and not with a volumetric source. I didn't know as much as I know now. So, but these are the results, and when you do it with a volumetric source, the results are very similar.
As a first order system, you're saying the results are better in them.
And infinite difference are better than pseudo-spectral. In this case, we can compare it, but for example, the wave propagation, so the spectral methods is very much better than finite difference. In this case, in boundary conditions, finite difference is much better than pseudo-spectral.
But I meant compared to not with the Euler formulation.
For the wave equation formulation, finite difference is much better than pseudo-spectral, and for the Euler formulation, we have very similar results, but it still wins finite difference. Let me finish, please. Well, summary, okay, this is very important. I want to show you. In pseudo-spectral, we have this. If you want to compute the spectral derivative of a special distribution, it starts here and ends here. You don't have periodicity. And when you do the Fourier spectral derivative, what you get is this, which is this phenomenon, you will get error. So what you need in your simulations, always independently of the domain that you have, you will have your source, your wave propagation algorithm, your boundaries, what you want. And at the end, you have to add these perfect image layers or absorbing modality layers in order to get some spatial distributions that starts and finish in zero, okay? It's very important this, because if you don't do this, you have this problem in the derivative. So at the end, let's forget this for esto. If we compare the methods here, the main features, this is based on finite difference, this is on Fourier transform. Propagation, we have angular dependence in the finite difference, the dispersion error. And whereas in pseudo-spectral method, we have isotropic dispersion error, which is very good. This is a very good point in pseudo-spectral. In source generation, we have more flexibility maybe in finite difference than in pseudo-spectral. In pseudo-spectral, we need volumetric sources if we want something good. And in boundary conditions, finite difference works much better than pseudo-spectral. For the wave equation, we have an hybrid formulation. And for the other equation, it works good, but not better than finite difference.
But the tests are not full for the pseudo-spectral because you didn't put the volumetric source yet.
No, but you cannot work better than finite difference. At the end, you will work as finite difference. That, for example, propagation that you are better because you are isotropic in pseudo-spectral than in finite difference. I'm trying to compare if at the end pseudo-spectral is much better than finite difference. Well, it depends on what problem are you treating, okay? And the specifications in finite difference we don't have it, apparently, and we have the gift phenomenon that we need to deal with it, and you have to take into account every time that you want to implement this. So, which method is better? Would be a clever question. Maybe it's not a clever question. Maybe it's not a good question. This is not the whole world of numerical methods and finite difference is better than no. What we have are tools, and we need to study these tools. And maybe in room acoustics, so the spectral is not the best choice. Maybe it's better finite difference. But there are many other applications, like geophysical application, like now I'm doing things in human tissue, that it makes sense to work in pseudo-spectral because we don't have boundaries, like impedance boundary layers. We have a very simple domains. For example, if we want to compute fractional derivative, spatial fractional derivative, pseudo-spectral, It's trivial because you just make the Fourier transform, multiply by up to this fractional number and come back. It's different than infinite difference. You need to do a convolution, you lose a lot of time. It's very difficult. So maybe pseudo-spectral in this problem is not the best choice. We see the problems that we can get, but another problems can be very competitive. So it is at the end what we need, what we have to do as a researcher is to provide tools and to study tools and to develop in many different applications and to see how it works and which are better for depending on the problem that you do. So thank you very much.
Thank you for everyone who stayed, and if you want to stay longer, we still have time for questions, a couple of questions. Yes.
So I guess I got a little bit confused because you are talking about pseudo-spectral methods.
Yes.
But what you used was purely spectral, right? You use the Fourier transform. So usually people refer to pseudo-spectral, they do some, they want to deal with periodicity, they take orthogonal polynomials, for example. So you don't have to.
You said that maybe with Chebyshev or another thing, you don't have this. But you see, when you're programming, the FT is the most fast algorithm that you can have.
Right.
And this is maybe the reason, because at the end, we can take profit of these implementations, really optimize the fast Fourier transform and to use it in an algorithm, in a massive algorithm. And you can get always faster algorithms than using Chebyshev or other approximations. Not only for the mathematical point of view, there is because, for example, these problems from acoustics are massive problems. And you need to make fast simulations. And I'm sure it's faster Fourier transforms than.
There's a couple of reasons. One is this fact that there's spatial, that he's using it for spatial discretization. And then the other one is that there's actually a mesh. And the FFT is assuming, so it's not a Fourier transform of the full infinite dimensional thing. It's a Fourier transform of just a sample of finite number of points. So that's where the pseudo is used.
So the other, if I can just a second one. So you explained the boundary was a single word, right?
Yeah, an impedance boundary wall, yeah. Or yeah. It was like this, yeah. Something like this, it was like here, no? Something like this.
But was it actually?
This is a piece of the domain, okay? Is the.
But you actually have the piecewise smooth boundary, or just the simple?
Well, in this case, I have these impedance boundary conditions, and what we observed is that pseudo-spectral maybe is not a good method to work with these kind of problems that you have these impedance boundary conditions. But for example, if you are making a geophysical simulation in the ocean, you have the water, and you have a big piece of the ocean, and at the end you just add absorbing boundary layers. There are no boundaries like this. Okay. In these cases, for example, pseudo-spectral will work very good. We won't get these problems that we find in the boundary conditions. But it was a good excuse to face these room acoustic simulations, because mathematically it has all the problems. You have the source, you have a wave propagation, and you have these boundary conditions that you have to deal with.
And usually you have corners, right?
Yes, these kind of things. Yeah.
So there is this word by Gottlieb that has had that this is filtering.
Yeah.
To get rid of the Gibbs phenomenon. So I'm wondering, because that's really what brings you in a disadvantage with the finite difference method.
Yes. Totally.
If you do some filtering for Gibbs,
yeah.
Then you can achieve some spectral accuracy, maybe. Right?
Maybe, yeah. What I decide is to get far from problems that has these boundary conditions and to work with problems with no boundary conditions, because I think you have to do something more than what you do in finite difference if you want to get some accuracy. Is what I get. Yeah. So, but there are a lot of problems that pseudo-spectral, and it is not required in boundary condition, and you get a domain, a very simple domain, and in that cases, pseudo-spectral Fourier methods are appropriate. But as I told you before, maybe for room acoustics, I wouldn't use these methods of the spectrum. It's useful to understand which problems you find when you're trying to do things, but I would use finite difference with a more accurate finite difference operator, but I would use finite difference because they have developed very good this problem of the boundary conditions, of the impedance boundary conditions. There are many ways of doing for the wave equation, for the wave equation. They have many formulations and they work very good. But it was my PhD. I need to do something new, and I tried. And well, sometimes conclusions are not always this is the best. A good conclusion is to say maybe it's not good for this, and let's see for what is good this method. So, but yes, a lot of problems. This part of here provides a lot of problems to the method, and maybe you should filter something or to do something. And this point of here, we put to 0, for example. We didn't treat the corners at least.
I think misunderstood me. What I was saying is that there are some developments in pseudo-spectral methods where you can do filtering, you can actually deal with the Gibbs phenomenon. You can filter out these artificial frequencies.
How, bueno.
This is work that was done by Gottlieb.
Yeah. And how does Gottlieb? But they have something that is not periodic, but they filter somehow, and at the end they can compute the derivative. What you say at the end, no?
Periodicity you can deal by not, you can use the Fourier transform, but periodicity you can deal also with pseudo-spectral methods where you use forgotten polynomials.
See, but at the end, look, we are in the Barcelona Supercomputing. At the end, we want a very fast algorithm because it is a strong constraint. We work with another polynomial, mathematically are very nice, but implemented in a code, it's surely slower and Fourier transforms.
And this Gibbs stuff, it's like an attenuation factor or something like that. And is it in the context of pseudo-spectral methods for which type of boundary conditions? Do you remember? Or
I haven't looked at it, but I think it's pretty well developed in the literature. I'm not an expert on that.
No. Okay. I would be interested to have this reference. I would like to see.
Any other questions? Yes.
Why did you solve the wave equation in the time domain and you didn't solve the Helmholtz equation for many fixed frequency?
Because I was contracted by Telefonica and they want for me to make this analysis because they want to make it was some kind of video games. And they want to compute impulse responses at real time, and you have immersivity of the position and everything. Okay, and they want to explore the spectral method on these kind of applications, and Helmholtz equation and these kind of things are not used to compute impulse responses in rooms. I think this is why I use the only wave equation and these kind of things. You understand? No.
Well, sometimes time harmonic case, which will lead to the Helmholtz is.
But this used for the pseudo-spectral method for the Helmholtz equation is widely used. Yes. But they want they wanted to develop this for the wave equation only, and in the time domain and these kind of things. And it was my PhD, and then I get an expert in this, but no, I never do it for the Helmholtz equation, for example. But I think it works, and there are a lot of reference, and for the heat equation also. Yes, when they use it.
Yeah. So do you know if there is some sort of version of this pseudo-spectral method that works with variable sound speed, or?
Yes, I implemented also. For example, in the ocean, we develop to measure this full wave inversion when you want to get an image of the ocean for the geologist. What we do is putting on water is a domain without this wall, it's only this with these absorbing boundary layers, and the node here, each node has different density and velocity of propagation, and it works Perfect.
And those are.
But you take into account I think the lowest speed or the fastest speed, I think, which I don't know which of two, will mark you the stability and the spatial and temporal discretization. Only this. You have to see where is the smallest velocity, smallest or highest, I don't know. And one of these will constrain you the temporal sampling. But it works.
And are those usually faster than the finite difference algorithm?
If you implement it in CUDA with the fast Fourier transforms that they have, and yes, it would be faster because your size of your mesh would be smaller, but you will need to compute more times. But this is smaller. This is better than have bigger things and computing less time. Yes, goes faster. But it should be in CUDA. If you do it in CPU, for example, you don't see this gain. Pseudo-spectral has some subtlety. For example, if you want to work in one dimension, you do your code and you find a difference, you can work with a stability current number of 1. And the results are perfect in finite difference. Pseudo-spectral, you cannot work with stability number 1. You always work with 2 over P. And what you see in one dimension, you say, it works worse than finite difference. Goodbye, pseudo-spectral. You need to go to 2 dimensions, 3 dimensions, where the current stability number in finite difference is not 1, it's another number, it's less than 1, and you can start see the error in finite difference, you see the angle error in finite difference, and then you see that pseudo-spectral start to work better. But if you just work in 1 dimension, you will say, pseudo-spectral doesn't work better. Ciao, goodbye. You need to go in 2 and 3 dimensions. So sometimes, for example, this is the gate phenomenon that you find if you don't have periodic spatial distributions, you find this error. If you start with this method that you don't know too much, you can say at the very first time, you say, it doesn't work. It doesn't deserve the time that I spent. You need to go at 2 dimensions. You need to control these things a little bit. The source generation should be volumetric. If you don't respect these things, you will say this method doesn't work. Finite difference is very easy sometimes, and in 1 dimension, so the spectrum works worse than any method than finite difference, because finite difference can work with a stability number equal to 1. Is you obtain the analytic behavior. So. Questions? Okay.
Well, last round.
Thank you very much.